Your car makes tiny, timed fireballs in each cylinder dozens of times a second. So why does the engine feel smooth instead of like a jackhammer? The crankshaft's shape is the quiet hero. Let's open it up and watch. You press the gas and the car glides. Inside each cylinder, fuel and air burn in a fast, controlled way, not a blast that rips things apart. More like a clean torch that pushes a piston down. Thousands of these little burns per minute turn into one steady spin that does not spill your coffee. We will see the 4 strokes at work and the exact crankshaft geometry that smooths the punches into a calm rotation. Here is the first problem. In a 4-stroke engine, only 1 out of 4 strokes makes power. Nicholas Otto laid this out back in the 1870s. Intake, compression, power, exhaust. Only the power stroke pushes. The other 3 cost energy. The piston is moving, valves are moving, air is pumping, and the crank is still turning during those. But the burning happens only once per full cycle. A full cycle takes 2 turns of the crank. That is 720 degrees. In a single-cylinder 4-stroke, you get 1 push every 2 turns. Picture a person on a swing who gets 1 shove, then coasts 3 moves, then another shove. It would lurch. That is why a single-cylinder lawnmower shakes your hands at idle. If you could see the push over those 2 turns, it would look like one big hump, then lots of flat nothing. 1 strong moment, then 3 strokes of the piston dragging air or gas out. That is ugly for smoothness. The cure is to overlap many humps from different cylinders, so the sum looks almost flat. Meet the crankshaft. It is a bent steel spine with offset pins, called throws. The piston pushes straight down the cylinder. The connecting rod leans on a throw. That offset turns the straight push into a twist. It is like pedaling a bike. Your foot pushes a pedal down and the crank turns. Because the cycle takes 720 degrees, the piston being at the top or bottom matters. The throw angle tells you where the piston is in its stroke. When a throw is up, the piston is near the top. When it is across, the piston is mid-stroke. When the angles are planned, each cylinder reaches its power stroke at a different time. In a classic inline 4, the firing order is 1, 3, 4, 2. That means the throws are phased, so one cylinder starts making power just as the previous one is fading. The pushes overlap. You get a rope of small shoves, not one punch and a coast. This is the crankshaft trick. Let's run the 4 strokes in plain words. Intake. The piston goes down, the intake valve opens, fresh air and fuel rush in. Compression. The piston goes up, both valves are shut, the mix gets squeezed. Power. The spark lights it. Pressure rises, the piston is driven down. Exhaust. The piston goes up again. The exhaust valve opens. Hot gas leaves. The camshaft controls those valves. It spins at exactly half the speed of the crank. That way, over 720 degrees of the crank, each valve opens and shuts once. Many engines can shift this timing by a few dozen degrees with variable valve timing. A little overlap, where both valves are a bit open, helps sweep out the cylinder. The spark also has to be early. Fire takes time to grow across the mix. So the engine computer lights the spark before the piston reaches the top, often 10 to 40 degrees before top dead center. That way, the peak push arrives just after the top, around 10 to 15 degrees after, which is where it makes the best torque on the crank. Now, picture the pulses as a timeline. A 4-cylinder at 3,000 RPM has 25 fires per second in each cylinder. There are 4 cylinders, so about 100 fires per second across the engine. They are staggered by crank angle. The crank sees a near constant average twist. Double the speed to 6,000 RPM. Each cylinder now fires about 50 times per second. The engine as a whole has about 200 power events per second. Still staggered. Instead of a single thump per cycle, You get a woven train of pushes that smooth out when added. To ride out the gaps, engines use stored energy. The flywheel is a heavy disc on the back of the crank. When the crank speeds up in a power stroke, the flywheel soaks up a bit of energy. When the crank would slow during intake, compression, and exhaust, the flywheel gives that energy back. It bridges the non-firing strokes. At the front, a crank damper helps with twist. The crank is long and it can wind up like a spring along its length. A harmonic balancer is a hub with a ring and a rubber layer between. That ring lags a little and tames the twist. It is tuned to the crank's main twist mode, often in the low hundreds of cycles per second at cruise. Manual cars may use a dual-mass flywheel. It is like two discs with springs between them. The springs soak up little speed ripples and protect the gears. Automatics use a torque converter. It is a fluid coupling that also filters pulses as fluid swirls between two fans. We also have to kill the shakes from the pistons and rods slinging up and down. Big counterweights are built into the crank. They balance some of the forces so the block does not hop on its mounts. But an inline four still has a built-in up and down shake at twice engine speed. To fix that, many fours add two balance shafts. They spin in opposite directions at twice crank speed. Their little off-center weights push up when the pistons all push down, and push down when the pistons pull up. The forces cancel. Mitsubishi made this idea famous in the 1970s with the silent shaft. Crank shape also sets the sound and the feel. A cross-plane V8 has throws at 90 degrees with big counterweights. It fires evenly and feels smooth with that lazy burble. A flat-plane V8 has throws at 180 degrees. It acts like two inline fours joined. It revs fast and sounds raspier, but it vibrates more. Inside the cylinder, pressure gets wild for a moment. In a modern engine without a turbo, peak pressure in the power stroke can hit 50 to 80 bar. With a turbo, it can top 100 bar. The engine computer rides the edge of knock. It advances spark until a sensor hears trouble, then trims a few degrees to be safe. Important point: this is a fast burn, not a true explosion. True detonation is a shock wave that hammers parts. That is knock, and it is bad. The whole system is tuned so the flame spreads smoothly across the mix, reaches peak right after the top, and does not slap the metal. Let's put numbers into feel. At idle, say 700 RPM, a four-cylinder has about 23 fires per second across the engine. The flywheel and, in an automatic, the converter, average those into a steady idle. The hood does not hop if all four are lighting on time. Pistons are sprinting even when the car seems calm. With an 86mm stroke at 6,000 RPM, mean piston speed is around 17 meters per second. Most everyday engines aim to stay under about 20 to last a long time. Now think about that when you hear a gentle hum at highway speed. The crank floats on oil. It does not touch the bearings when running. Pressurized oil forms a wedge that keeps steel off steel. That oil film is hair thin, often 5 to 20 micrometers. Main bearing clearances are on the order of a few hundredths of a millimeter. The pump feeds hot oil at 2 to 5 bar and can move tens of liters each minute at speed. From the crank to the tires, the smoothing continues. The clutch or the torque converter adds some give. Gears, the drive shaft, and the axles all have some flex and some mass. They all act like small flywheels and springs. They help turn the raw pulse train at the crank into steady torque at the road. The exhaust and intake are timed to this pulse train too. When an exhaust pulse leaves, it can pull on the next cylinder's exhaust and even help draw in fresh air. Headers and intake runners are cut to lengths that make the gas pulses arrive when they help, not when they hurt. It is like traffic lights timed well through town. Here is a simple story from the shop. Why does a mower shake but your car does not? A mower often has one cylinder and one push per 2 turns. It needs a heavy flywheel to coast through the dead strokes. Your car has 4 sets of pushes overlapped, plus a damper and often balance shafts, so your steering wheel sits still at the light. Another one, a misfire you can feel. If coil number 3 dies on a 4-cylinder, you just lost 1/4 of the expected pushes every 720 degrees. You feel a steady stumble at idle. The flywheel cannot hide a missing shove that big and that regular. The whole car nods in a rhythm. High RPM is wild too. At 9,000 RPM, a 4-cylinder fires about 300 times per second across the engine. Yet, the belt on the front stays calm enough to spin the alternator and the pump. That happens because the damper is tuned to the crank's twist, and the pulses are phased just right. If you are enjoying how these little tricks add up, join Buildguts. Subscribe for more clear looks inside everyday machines. We keep it simple and real. Now step back and look at the whole machine. At 3,000 RPM, a 4-cylinder is juggling about 100 tiny combustions every second. Each one slams the piston with tens of bars of pressure. A shaped steel crank, often forged and treated for strength, turns those into smooth twist while it rides on a hair-thin oil film. The damper on the nose fights twist. The flywheel bridges the gaps. The firing order and crank throw angles make the pushes overlap. The shafts cancel shakes. The valves and spark hit their marks to put peak push right after the top. Put it all together, and those chaotic little fireballs become silk-smooth rotation that moves a 1.5-ton car without drama. That is the crankshaft trick. Hidden, simple in idea, but tuned to the last degree. If this hit that, "Oh, I get it" spot for you, subscribe and leave a like. There is more on engines, bridges, chips, and power on the channel. Take it for a spin, and see you next time.